Interesting problem. So basically, if you read this problem, there's a lot of stuff here. Basically what they're saying is they exert a 5 Newton force on both of these for 1 second. Okay. Let's not worry about the seconds right now. Because, by the way, in here and in here, so they say between 0 and 3 seconds, but the only thing that place anything's happening is right here. So if I apply a 5 Newton force to each of these, ask yourself, are they going to accelerate at the same rate? And the answer is no. This one's going to accelerate at half the rate, right? Because the more mass, right? F equals ma and all that. So let's take a second. Let's figure that out. So the force on each is 5 newtons. So we're going, for each one, we're going to do force equals mass divided by acceleration, or if you like, let's just solve for acceleration. Acceleration is going to be equal to mass divided by force, which for this one is just going to be, so the acceleration on this one is going to be mass is m divided by the force is 5 from the graph, 5 newtons. Great, there's your acceleration. About this one, its acceleration is going to be its mass, which is 2m, also divided by 5. All right, so a quick note will be that this, let's see, maybe I get this right. I'm going to make sure I do Africa. No, good Lord Almighty. I should go back and just turn in my physics card. Obviously, it's 10:30 at night, although I have not been drinking. Really, I haven't, just that. So, what the heck was I writing? How many of you were like, well, when you lost your mind, F is equal to ma? I got all disconfabulated, but I knew something didn't make sense when I saw the answers there. So let's try that again, shall we? A is F divided by m. There we go. So that is, for this little guy, A is 5 divided by m, and for this guy, the acceleration is 5 divided by 2m. This makes more sense. This is a smaller acceleration, which is what I would have expected. Bigger object. When I saw these answers, I knew something was up because this was bigger than that, and that made no sense. See, so even though I was clueless and I wrote down the equation, I caught it pretty quickly. That's my excuse. So, what we need to know is power is going to be the work done or the change in energy. So I need to know, how does this acceleration affect the change in velocity? Well, we got this. The velocity for the single mass after the acceleration is over is going to be its acceleration times time. I think they both started from rest. Yes. The velocity for the 2m one is its acceleration, so I'll call this am, times the same amount of time, 1 second. All right. So, but a for the single m mass is going to be 5 over m. So this, its velocity is going to be 5 times 1 second, right? Divided by m. So it's really just the same thing. This is also going to be whatever it was up here, because the time is 1 second. So that's going to be 5 over 2m. Okay. So this is the final velocity of the small block. This is the final velocity of the large one. Which one has a bigger change in kinetic energy? Well, they both started at 0. So we really need to find the final kinetic energy for m and the final kinetic energy for 2m. Okay. And whichever one is bigger, that's going to be a bigger change in kinetic energy, and power is change in energy or work done, which, by the way, bigger change in kinetic energy is going to need a bigger net work done, divided by time. And we already have the time factored in here because of the 1 second. So I wouldn't worry about that too much. What we're really looking at right now, since they're both 1 second, is which one's got the bigger change in energy. So let's take a second. What do we know so far? So I got kinetic energy for the single mass is going to be 1/2 times its mass, m, times its velocity, which is this 5/m, squared. The kinetic energy for the 2m is going to be 1/2 2m times 5/2m squared. Once again, the squared is going to make all the difference. So for the little guy, I get kinetic energy, and therefore the change in energy, because it started at rest, the final kinetic energy of 25, that's going to be that squared. It's going to square the m, so one of them is going to cancel, so over 2m. Over here, I'm going to get, well, it's going to be 25. This is going to be, let's write it out. So this is going to be 2m times 25 over this 2, which is in the bottom, times 4m squared. Because when you square this, you're going to get 2m times 2m, which is 4m squared. Let's clean this up. That's going to be, well, these 2's are going to cancel. So I'm going to have, and this m is going to cancel with one of those, so I'm going to have 25 over 4m. Now, you could go ahead and do the division if you like. This right here is, we could, if you wanted to, you could write it as 12.5 m. This one is going to have a final kinetic energy of, what's half of 12.5? 6.25? 6.25 m. This is going to have half of the kinetic energy. So even though they had the same force over the same period of time, more power was generated here on the small one because it changed the kinetic energy, and speed matters more with kinetic energy. It gets squared. So a small object going fast is a better bet for having more kinetic energy than a big object going slower. There's a long way around on that one. There's probably another way to do it when we get to momentum. I think the same problem comes up, or a similar one. We'll look at it again. All right. 12. Block of mass 3 kilograms slides along a horizontal surface that has negligible friction except for one section, as shown above. The block arrives at the rough section with a speed of 5 meters per second and leaves it a half a second later with a speed of 3 meters per second. All right, what is the magnitude of the average frictional force exerted on the block by the rough section? So actually the easiest way to do this, I'm trying to debate. So the easiest way to do this is actually using something called impulse, which is in the next unit. I'm going to preview that, but I'm also going to look at it a different way. There's probably at least 2 or 3 different ways you could look at this. I think we're going to look at it like this. We're going to, first of all, without using impulse. See, I need to know if I'm going to get force from energy, I need distance. And they don't tell me the distance. But they do tell me this. If it comes in at 5 meters per second and it leaves at 3, what's its average velocity? What's its average velocity during that? It's literally going to be the average of those two, right in between them. So that'd be 4. So its average velocity is 4 meters per second. Okay? It travels for 0.5 seconds from here to here. So we can look at it as if it traveled at 4 meters per second. Yeah, I know it was traveling faster here, but it was slower here, so it really works out. that it's just like as if it traveled this section at 4 meters per second, constant velocity, for that much time. So we can play that little game. So the distance, this distance here, is equal to, let's see, so rate times time. So speed, in this case average velocity, times time, which is going to be 4 meters per second times 0.5 seconds. So this distance is 2 meters. All right. I'm feeling a little better about things. Now that I've figured out that distance, what's the change in kinetic energy? Well, the kinetic energy here, kinetic energy initial, is going to be 1/2 m, which is 3, times 5 squared, 25, right? Over here, the kinetic energy final is going to be 1/2, same 3 kilograms, times 9, 3 squared. So this is, we got this, 1.5 times 25. 37.5 is the original kinetic energy, joules. And over here I got 1.5 times 9, 13.5. So the final kinetic energy is 13.5. So my change, so the first step here was use average velocity to find the distance. Then, unrelated, at least initially, find the change in kinetic energy. And that's going to be 13.5 was the final kinetic energy minus the initial, which was 37.5. Kinetic energy dropped by 24 joules. That is equal, whoops, sorry. Okay, so we're going to use average velocity, that concept, to find the distance for the rough section. We'll come back to that. That was 2 meters. Find the change in kinetic energy. Did that. Next thing, change in kinetic energy is equal to the net work done, which is to say that the change in kinetic energy is equal to the force times the distance. And the force is what they want. And I know the distance is 2 meters, and I know this change is 24, so I do 24 divided by 2, and that force was negative 12, negative being left, sorry, 12 newtons. They probably don't care about the direction, yeah. It's going to be that. Now, looking ahead to the next unit. Next unit is about momentum. Momentum is simply mass times velocity. Change in momentum, then, is your final mass velocity minus your original. That's easy to do here, right? It's 15, and this is 9. Cool? Oh, sorry, pointing at it and you can't see it. All right, m times v here is 15. This is 9, right? So I know that the change in momentum is 9 minus 15, that's 6. That's a drop of 6. The units of momentum are kilogram meters per second. They don't have a fancy name. It's that. So I lost, so I did mv final, which is 3 times 3 kilograms. So that's 9 minus the original, which would be 5 times 3, which is 15, and that's where I got this negative 6 from. All right, so that's a quick introduction to momentum. Change in momentum, so you know how change in kinetic energy can be looked at work? Well, change in momentum is equal to something called impulse. And another way to look at it, turns out, is that it is the force on the object, times the time. So unlike energy's force times distance shows up with work, momentum has this impulse thing called force, which is calculated by doing force times time. So this is the impulse. So there's 2 ways to look at it, change in momentum and this. So I know that that's negative 6 kilogram meters per second is the change in momentum, the impulse. That's equal to force times time. The time is 0.5 seconds. If I divide by 0.5, Half into 6 is that's negative 12. Hey, look at that. A little easier with momentum. Momentum makes a lot of things easier. The only problem with momentum, as we'll find out later, is it's a vector. Which means angles and all that negative and positive mean direction, and it's a little harder that way. All right. But this approach, that momentum is a better approach for this. You can do it without it, but momentum is an easier approach. What is the magnitude of the work done? Oh, well, wait a second. We know that. I figured it out right here. Because the change in kinetic energy is the work done by friction here. So if you didn't know momentum, you would actually have to do 13 first, in a way. You wouldn't realize what you're doing, but you would have to, before you get that first and then go back and do it. So the 24 joules, the change in kinetic energy, is the work done by friction. By the way, that was 13. I lost my 13. That was 13. All right. Now we're going on to 14. An object of mass m is attached to a spring on a frictionless inclined plane that makes an angle with theta with the horizontal as shown above. The object is released from rest. The spring is and the unstretched position as the object moves to along the plane. Its displacement from the unstretched position is x. I know I've done this one in one of the help sessions. I know I've recorded it before. So let's hope I do as good a job this time, or maybe even better. I'm probably not going to do as good a job because I'm at the end of this section here and I want to get through it. But there's there's two ways to look at this. So really, we're only concerned with from here to here, right there. So let's just focus in on that real quick. So method one, we'll call it. Method one. Method one, the block goes from here to here over the distance x, stretches the spring as it does. Now, theta. Method one, we tilt our heads and we look at this as our x-axis and this is our y. You can put the y-axis anywhere you want, it doesn't really matter, but we look at this as our x-axis. And so we say, all right, well, it moved a distance x, so I know that work done, right, is equal to force times displacement, and there's my displacement. The question, and what makes this one trickier, is where the theta and all that is, what's the force pulling on it here? Well, it's not all of gravity. If you remember, gravity in this case pulls straight down. Only a portion of the gravity pulls down the ramp like this. And this is where I would expect you to go back and be able to remember this. This is, you know, so the weight, I guess, yeah, the weight, the parallel component, the part that pulls the thing down the ramp, not into the ramp, turns out to be the total weight times the sine of that angle. And even though I know it's in the x, remember inclined planes are one of those we're going to switch, so this is a fact I would expect you to know for inclined planes. Period, end of story. That is our force. So work done would be that force, mg sine theta, times the distance x. We look, see, and I think that's one of the answers. There's another way to look at this, though. It would be helpful to understand energy, and it might make the whole thing easier. I don't know. For some people it will. For others it won't. So same situation. Block moves. So this is method 2. Here, theta. Here we're just going to look at the fact that the block moves from here I guess we use the back side of the block. From here to, well, we'll put the back side of the block all the way down. Hold on. I'll find my eraser. There we go. So, yeah, they use the back side of the block. So, okay. So we'll just worry about it from there to say here. Cool. And this is your X right here. Cool. There we go. And so what this method does is it says, I'm not going to tilt my axes. Gravity acts up and down. I'm going to stick to my regular axes, and I'm going to look at the y dimension. Gravity only pulls down. So the only displacement that matters for gravity is from here to here. It doesn't matter that it went over. Gravity only cares about the fact that it went down. Gravity, any displacement perpendicular to gravity, gravity's force, gravity can't do work. So we want to look at, well, how far is this distance? I know the force here is just straight up mg, not any component of it, because we're now looking at it straight up and down. Gravity pulls straight down on the thing. How far is this? Well, I know this is x. I know this is theta. I want this distance. That's the opposite side. So you go SOHCAHTOA on that thing, and you find out, you realize that the sine of theta, no surprise there, is equal to the distance I want, I'll call it d, divided by the hypotenuse x. So the distance in the force times distance is equal to x times the sine of theta. What's the force? So remember, the work done by gravity in this case is the force of gravity times the displacement of the distance. That's going to be mg, but this distance, looking at it from this perspective, is a shorter distance given by this. Hey, what do you know? Mg x sine theta, same set of stuff being multiplied as it was earlier, right? We have not broken physics, it's the same answer. And that answer would be mg x sine theta be, yep, this guy right here. Hey. All right, 15. Last one. Object of mass m is initially at rest and free to move without friction in any direction on an xy plane. Constant net force of magnitude F is directed in the positive x direction and acts on the object for 1 second. Immediately thereafter, a constant net force, okay, let's just go with that first. Let's just go with this one. So what does it mean in terms of kinetic energy if a constant force acts? Constant net force. Okay, so constant net force means the thing's going to speed up, right? So velocity is going to increase. In this case, speed up. It's at rest. So that means that it creates an acceleration, which is equal to change in velocity. So a net force creates an acceleration, and that's equal to the change in velocity over time, and that's a linear change. Constant acceleration is a linear change. So the velocity increases from 0 to some value in a linear fashion. But kinetic energy is 1/2 mv squared. If this goes up as a linear way, I'm squaring it. So the graph of kinetic energy under those circumstances would not be a line. It should be a parabola. Parabola looking thing, right? All right. So I'm looking for just from 0 to 1 second, this interval. I'm looking for something that looks like one of my answers should have a parabola. Okay, so this is so far, okay, this one is in the running. It's got a parabola, a little sectional. Let's go find the other answers. Here we go. 0 to 1, and it's got a parabola. 0 to 1, and it's got a parabola. Zero to 1, that's a straight line. Nope. This one's right out. This one's like, what? No, 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 no. Is all I can say. No. No. Why? Because this one says that the thing didn't even start at rest. That it started with a kinetic energy that was something other than zero. Well, if you're at rest, you don't have a kinetic energy that's something you're moving. Right? If you have a kinetic energy, if you're at rest and you're not moving, you have no kinetic energy. But that's not what this says. So, this one's right out. Like, no. Okay. So we can roll out the last page. Now comes the interesting part. So, while this thing is... So you've applied this force. This is the part that I think the trickiest part of this whole thing. Is you've got this object and it was at rest on the XY plane. And after a second, you were pushing it in the X direction. It's some distance. We can figure out how far. I'm not really worried about that. But it's got some velocity and some kinetic energy this way. But it's got a velocity this way. And then at that point, you start pushing on it. You start pushing on it upward. Now, here's the most important part of this. Is as far as an upward force is concerned, does this velocity make a difference? And the answer is no. If you recall, like if we throw an object horizontally, it drops in the same amount of time that an object dropped would. Because this velocity is all in the x, and gravity doesn't work in the x. So this y velocity, this y force, is going to speed it up in the exact same way as if it was at rest somewhere, or it doesn't even pick up anywhere. But so it picks up speed in the exact same manner that it did horizontally, vertically. So, and does kinetic energy care at all about direction? No. All it cares about is you picked up speed. So when you apply that force there, it ends up, it might end up being, it'll be up in here somewhere later on. But here's what's the important part. It would have picked up the same velocity in both. So it would have picked up this amount of kinetic energy and then this kinetic energy. And this is exactly the same as this. So which one of these graphs shows the same thing twice in a row? This goes here to here. And then, what is it, for another second? Right? And then it not only does it show this is not the same as that, really, it continues to change. But after 2 seconds, there's no more forces on it. So the kinetic energy shouldn't change. So that's what makes me rule out this one. It might have been a little bit convincing if they'd have done that. Finished it off at the same... Maybe I'd have been like, well, this looks the same as that. I could see that being a little confusing. But this is your telltale right here. After the second, there's no force on it. There's no way it can keep accelerating. So we'll rule out that one. But it's not the easiest one to rule out. All right, so we said that the change is kinetic energy is going to look exactly the same. Well, it's here, isn't it? Right? Boop. And then this one changes the kinetic energy the same way, and then there's no force, so it keeps that. This one is not the same. This is weird. That's like a square root, that means that means the kinetic energy doesn't increase as much towards the end. But if it increases velocity, no, this just doesn't make any sense. I could see being confused by it, but this is a better choice. All right, this is a better choice. It looks exactly the same because as far as the vertical force is concerned, moving horizontally doesn't matter. So it increases the speed vertically in the same way that the horizontal one did. And so these two changes in kinetic energy should be the same, looking in here. And should be the same amount, too. Okay, I think that's it. All right, I'll try to get 2 done as well.